In this lecture, we are going to go over two ways to calculate entropy for reaction. And our two ways are actually going to give us slightly different answers. So there's that. So we're looking at ammonium gas and oxygen gas combining to form NO, which I forget the exact, if it's nitrous oxide, nitrous oxide, anyway, and water gas. And so we have a balanced equation here, although it looks like my subscripts were lost when I copied it over. And we're going to try to calculate it from its enthalpy of the reaction, and then we're also going to try calculating it using standard enthalpies. As I said, we'll probably get different values here, and that's because these standard enthalpies and the enthalpy of the reaction were probably done at different temperatures. So let's start with A. We're told the enthalpy of the reaction, so that's that change in enthalpy, is equal to negative 905 kilojoules per mole. So we know that piece. We also can pull up our equation for the change in entropy for reaction. So that delta S for reaction will be equal to the heat that's transferred for the reverse process divided by temperature. So thinking about what that heat of the reverse reaction is. So let's, the opposite of that would just be the heat of the forward reaction. And so that heat of the reverse will be equal to the negative of the heat of the forward reaction. And this we've seen, this is just we've seen this before. It's really just the heat of the reaction. So if it's the negative of that, and we know that enthalpy of a reaction is equal to the heat of the reaction, and this is going back to when we talked about thermochemistry, that reverse reaction will really be the negative of our enthalpy for the reaction. So I'm going to rewrite my equation for entropy. I'm actually going to make it the negative of the enthalpy of my reaction divided by the temperature that we're talking about. So we are looking then at plugging in our value that's given, and we know our temperature as well. I believe on this one, and sorry, it's not on here. Let's assume 298 Kelvin. So assuming that we're at room temperature, we will calculate the change in the enthalpy for the reaction to be that negative of negative 905 kilojoules per mole divided by my temperature of 298 Kelvin. And that's going to give me a value of 3.04 kilojoules per mole Kelvin. All right, so that's one way. Now let's take a look at calculating it with standard entropies of reaction. And I use the reference table that's in your lecture notes that came out of a textbook. And so my first step really was to look up the values for our standard enthalpies. So for ammonia, let me look it up, it's 192.5. For oxygen, it is 205.0. For an O, it is 210.62. And for water, it's 188.83. And the units here are all in joules per mole Kelvin. So what we're going to use for an equation then is we're going to take the sum of the coefficient times the standard entropy for the reactant for each of our products. And from that, subtract that entropy for our reactants. So it's that sum, we take the coefficients, we multiply it by the standard entropy for each of the reactants. And that should give us our value. So switching over. So I'm really just going to plug in the values I pulled out of a table. I'm going to make sure I include the coefficients from my balanced equation as well. And I've got these right here. I've got 4, 5, 4, and 6. So let's set this up. So in this case, my change in enthalpy is, or sorry, entropy. Entropy and enthalpy are easy to flip if you're me, unfortunately. I'll try to watch that. So we're going to start with our products. We're going to take our water and we're going to multiply that by our coefficient of 6. And add to that 4 times our 210.62 joules per mole Kelvin. And then subtract the sum from our reactants. So let's start with our ammonium. We've got 4 of those, and we have a standard entropy value of 192.5. And we'll add to that 5 times our value for the standard entropy for oxygen, which is that 205. And I ran out of room for my units. I apologize for the last one. Now we just plug this into our calculator. And when we do that, we calculate a value of 1,975.46 minus 1,795. We're going to get 180.46. So really this is 180 joules per mole Kelvin.